The next talk is going to be by Scott Irwin, who's a senior developer in Bloomberg.
Thank you. Thank you. So today we're going to talk about Dunder methods and why they are special. So we're going to cover pretty quickly what special methods are, talk a little bit about what the Python documentation calls basic customization. Then we're going to dive in, and we'll cover some of the Dunder methods, some of the special methods there, and then we're going to go more into some special cases like callable, look at numerical operators, and then finally we'll finish off with protocols, or at least a couple of the protocols. One thing to keep in mind is there's 40+ special methods, so there's no way I can cover all of those in this talk, so I'm cherry picking a few. So special methods, what are they? So special methods are the name used in Python documentation. You might also have heard these referred to as magic methods or Dunder methods. And for those of you that haven't heard the Python slang, Dunder stands for double underscore. The official definition from the Python docs is special methods are Python's approach to operator overloading, allowing classes to define their own behavior with respect to the language operators. So one example is Dunder add method, which is called by the plus operator and is defined by various built-in types such as int, float, and stir. So why are special methods useful to you as a developer? They enable you to give your custom types, your classes, to have the same features and expressiveness as the Python standard types. So one general note is when you're emulating a built-in type, you should generally only implement the special methods that you need, which is to say, if you are in your own application, you shouldn't necessarily worry about completeness. You should just care about what you need to get your application running. Now, if you're a library writer and you are accepting things from other people, then you might want to pay a little more attention to completeness. If you want to block specific functionality, you can essentially set the special method in your class to be none, and then that will prevent that type of operation. One example would be there's a special method Dunder reversed, which allows an optimization for reverse iteration across sequences. If your sequence doesn't support efficient reverse iteration, then you could block that by setting Dunder reverse to none. So basic customization. So what is in the basic customization? So one of the ones is if you've written any Python classes at all, you have seen this special method. And this basically takes an already instantiated object and fills it in. So this should not have a return statement because within the language, it's a type error to return anything other than none. And since in the Python world, if you don't have a return statement, the default return type of your function is none, best thing to do is to leave the return out. One little note is if you have a derived class and you want to make sure that you are using the base class and initializing there as well, you need to explicitly call the base class Dunder init function. So that's what this little bit of code down here is showing the base class and then the derived class calling the parents class Dunder init. Also in the basic customization is Dunder repr. This is the official string representation of an object. If possible, and this is from the documentation, if possible, it should look like a valid Python expression. This is the string representation that is typically used for debugging. So it should be information rich and unambiguous. So if you have spent any time at the Python REPL and you've typed a variable name and then watched what the values get dumped out, you've invoked Dunder repr. A closely related special method is Dunder stir. This returns an informal, or you could think of it as a pretty print string representation of your object. But this is the one that is called by the stir constructor, also by format and by print. But you don't necessarily need to implement this on your class because the default implementation that's inherited from the Python base object will call Dunder repr as its default implementation. One of the other things that you might want to think about is implementing Dunder bool. This defines the truthiness of the object. Generally, this should return true or false. But if you don't implement Dunder bool, the Dunder len method is called. So for containers, this is why an empty list, an empty dictionary, an empty set return false, is because they call the Dunder len method for those classes. And the truthiness is if len returns 0, it's false. If it returns any other value, it's true. Now, if you don't implement either of these methods, then all instances of your class will be considered true. And so here in the, we have a class swallow, and we're keeping track of the state of this swallow, and we are only true if we have an unladen swallow. There are some additional customizations, way too many to go into. There's some more around representation, such as Dunder format and Dunder bytes. There's what the documentation calls rich comparison methods, which is the less than or equal to, so on and so forth. And then there are some advanced Dunder methods, such as Dunder new, Dunder del, and Dunder hash, which you should only be implementing when you really know what you're doing. You can get yourself into serious trouble with those three. So with that, let's move on to callable. So the definition of a callable is any object that can be called. So a little bit of a recursive definition there. But basically, it's any object that supports the paren operator, which is to say it can be called like a function. Python callable objects that you might be familiar with are any of the built-in functions. Any function that you write yourself is a callable. The class objects that you define are callables. Methods on built-in objects. And methods of your classes that you define. All of those are callable. One additional thing, and this is where the special method comes in, is if you've defined a Dunder call method, then objects of your class are also callable as a function. So what does that look like? So informally, what you end up with is being able, here we're creating an instance of this multiply by, and then we're invoking that instance with arguments, just like we would any other function. And where you might want to do this is if you want to create a function with state. So here we've given it a state of 3. So this function always multiplies by 3. I could create other instances of this same class that multiply by something else. And I can have all of those active in my system at the same time. Next up are the numerical operators. This allows you to emulate numerical types by defining these methods. So they're the operators, the plus, minus, star, single slash, and double slash. We're talking strictly Python 3 here. And those dispatch to Dunder add, Dunder sub, Dunder mul, Dunder true div, which is true division, versus Dunder floor div, which is basically the integer style division. There's a bunch more methods that are available if you really want to go and implement a fully functional numerical type. There's matrix multiply, mod, div mod, pow, left shift, right shift, and the bitwise and XOR and OR. if you're not going to implement it, or I'm sorry, if you are implementing it and you're not going to support a particular style of argument, you should return not implemented. So if you have, say, your numerical class and somebody gives you a string object and you don't know how to add a string object to your object, you should return a not implemented. There's also this concept of reflected operators. All of the numerical operators have a reflected version. So where we had Dunder add, we have a Dunder R add and a Dunder R sub, and et cetera. The right-hand operand of an operator, its reflective operation is called if the left-hand operand does not have the supported operation, or returns not implemented. So one of the ways to look at this is if we look at an example. So here we have A star B. First, it will try to call the mul method on the A object, giving B as the argument. If that returns not implemented and A and B are different types, then it will call the rmul method on the B object, passing it A as an argument. And where you can see this in regular Python is that's how this duplication of string methods work. The int doesn't have a mul method that takes a string, but the string has a mul method that takes an int. There's also augmented assignments. Nearly all of the numerical operators have an augmented assignment, which is to say an in-place version, which is where the I comes in here. So we have I add, I sub, so on. The only one that does not have an in-place version is divmod. And these are the things that implement plus equals, minus equals, so on and so forth. Generally, these methods should do the operation in place, which is to say modifying self and return the result. That said, while the result could be self, it doesn't necessarily have to be self. And one of the places where you would see this in one of the basic types is integers. The instances of integers are immutable. So if I do a plus equal operation, it's going to do the operation and return a new object. So if I do 42 plus equals 1, I'm going to get not self of 42, I'm going to get a new object, 43. There's also fallback behavior. If there's no in-place version available, the operator falls back to the normal method. So if your class does not support plus equals, essentially it would break down into one of these two, where it would do the assignment and do the add or radd, depending on what the types are here. So an example of that is the stir class does not implement an imul method, but it does support the star equals because of this fallback behavior here. There's lots more operators. Some of these are the unary negative, unary positive, abs, invert, so on and so forth. If you are interested in these are well documented in the Python documentation. So on to some more complicated things. Let's talk about protocols. So a protocol, or let me back up. So protocols, everything that we've seen up till now, we could get away with implementing one and only one special method on our class. If we wanted our class to only support add, we could do that. For protocols, these are sets of special methods that we would need to implement in order to fully implement the protocol. Python has multiple protocols that you can use to tap into. Some of the most common protocols are things like collection and iterator. They're so common that the Python has a module collections.abc, which is to say abstract base class. that will help you implement these. It will guide you towards implementing the necessary methods to implement the protocol. So let's take a quick look at those two things. We're going to look at collection first. So a collection is a sized iterable container class. Special methods for the collection include Dunder iter, which returns an iterator for that collection. It also needs to support the Dunder contains and the Dunder len method, because remember we're supporting sized here, so we need to be able to know how big we are. So these slides are hosted on GitHub. There is also an implementation of this linked list class in that same repository, where these examples are coming from. So here I'm pulling in the linked list. I'm instantiating a linked list, and then I'm just quickly adding some things here, and then I can do things like sum on the linked list. And this works on my linked list because it's just using the underlying iterator. And I can do testing of contains. That's what in is calling the Dunder contains. And then lastly, len calls Dunder len. So what does this implementation look like? So the Dunder iter just returns an instance of the linked list iterator class is instantiated with the particular container we're working on right now, basically self of the linked list. Contains is just going through the list. Again, it's using the iteration. It's doing this is essentially causing an iteration, and then I'm just searching through. And then lastly, the linked list class happens to keep track of how many nodes, so the len operation is very efficient in this particular case. So a sequence, methods for sequence containers, they are everything that a collection is, plus get item, which is the square brackets. It could also include, optionally, reversed index and count. Some additional methods if you're going to have a mutable sequence. So this is like tuple versus list, is set item and del item. And then there are several more optional methods that you might need to implement. All of these are documented in the collections.abc documentation. But again, I'm going to remind you that you should only implement the minimum necessary functionality to suit your application within, or your use case within your application. For mapping, mappings are also containers, so they start with a collection, but then they also support get item, iter, and len, but they also include things like contains, keys, items, values. So basically, it should work similar to a Python dict. For additional methods, if you wanted to have a mutable mapping, you would need to have Dunder set item and Dunder del item. And there are several other methods that you could include, such as clear. An iterator is an object that iterates over an iterable. An iterable needs to implement the Dunder iter, which we saw before in the container. The iterator needs to implement Dunder iter as well, but it just needs to return itself. So if you call iter on something that is an iterator, it just returns you a reference to itself. But an iterator also needs to implement Dunder next. And the Dunder next is basically how you step through the iteration. And it should return the next item from the container. And when you reach the end of the container, it should return a stop iteration. It should raise a stop iteration. And this is the internal workings of Python are very much reliant on this. So let's take a quick look at the implementation for the linked list iterator. So Dunder iter is very easy to understand. The Dunder next is basically if we're an empty list, there's nothing to do, or if we're already at the end of the list. Otherwise, we move on to the next position, and then we return the data of whatever position we're at. And this is just conforming to the definition. So some examples of iterator behavior. So again, here we're just quickly building up a linked list. And then we're getting the iterator on that linked list, and then we're getting the next item. And then we're getting the next item. So next here is calling our Dunder next to make this work. When I get to the end of the list, I get the stop implementation or stop iteration exception. And that is used implicitly by the for loop. If you were to iterate, or if you were to do a while x in blah, blah, you would see that. So inclusion, we have special methods are Python's approach to operator overloading. And they enable your custom types to have the same features and expressiveness as the Python standard types. So essentially what the Python language has done is expose the inner workings and hooks to allow you to write very fully featured expressive code with your own classes. References, this is a direct link to the language reference, and then this is the link to the slides. The GitHub repo is basically SJ Irwin, or github.com/SJ Irwin, which I should have put on the slide, but I forgot. And that's it. Thanks. So we went a little fast, so I have time for a few questions.
Time for one question if someone would like to. Yay, question.
Hello, and thank you. Is it working? Okay, just carry on. All right, thank you for this amazing talk. I would like to just ask you one question in regards to it. You have given us examples of what actually caused this next Dunder method under the hood, like a for loop, like a while loop, etc. But I was thinking, I think generators, they also call when you call a yield, for example, it actually calls the next under the hood as well. Is that right?
Yes.
Yeah. That's all. Thank you.
Thanks.
Any other question? No? Okay, everyone understands. Oh, yeah.
So I think operator overloading and things like that has a lot of scope for horrible, horrible things to be done. Do you have a story of the most awful overloading that you have seen?
I think I'll keep that private. I don't want to embarrass myself or anybody else. I think this gentleman on the end had a question. Oh, same question.
All right, so if there are no more questions, there's a coffee break for 20 minutes on the 7th floor, and there is also going to be a book signing by Ian Oswald. So, thank you.
Thanks.